Hey, welcome to another Statics with Python problem. So in this problem, we're going to deal with trying to find a resultant force for a system of forces that are acting on this beam right here. And in order to do so, we do need to know what a force couple or a force moment couple system is. Now, if you don't know what that is, or that just does not seem familiar, I would highly recommend you go to the Statics playlist that I have and look up the force couple moment system videos there. But I will do a very quick review on what that is and why we would need it to solve this problem. So let's start off with the problem statement, and as always, there's going to be 3 videos in this problem. The first one, which is this one right here, it's just the problem statement and going over the statics that we need to solve this problem. The second one will be the algorithm and determining what we need to do for the code. And then the third video will be the actual Python script that we write code for, and we use that to solve our problem. Okay, so to start off, we have a beam right here, and it is supported at A with a pin and with a roller at B. And on this beam, there are a bunch of vertical forces, in this case, all acting downwards, and each force is some distance x away from point A. Now, our positive axes and our positive directions are right here, so x to the right is going positive, y upwards is positive, and anything rotation-wise, such as moments, going counterclockwise is positive. So always remember your coordinate system and which way is positive. So let's start off with sort of step 1. Actually, let's start off with the problem statement. I totally forgot the problem statement. Okay, so problem statement says there are n number of vertical forces acting on this beam AB, and we essentially want to write a Python script that determines the magnitude of the resultant force and the distance that that force acts from point A. So we're essentially looking at the system of forces that are placed on top of this beam, and we're trying to find the resultant force of all of these forces. And that resultant force is going to be at some distance away from A, or from point A, and that will just be some distance x, and this will be the resultant force. And so what we're trying to do is we're trying to find r, and we're trying to find the location of this resultant force. Now, when we look at this problem, we need to be very, very sure what this problem is asking us to do. You might be thinking, okay, well, if you have all these systems of forces, all these F forces, well, you would ultimately need to somehow calculate the reaction at A, the reaction at B, and then figure out the resultant. And that is incorrect. So remember, we are trying to find the resultant of these forces. So we're only studying that system of forces that are shown in this problem. And for force couple systems, we essentially need to reduce this system of forces into an equivalent force couple. And so the idea is take all of these forces and reduce them to one single force and one single moment acting at some point that we choose, and we use the force and the moment at that point to figure out what the resultant force is. So again, we are solving for the resultant of the given forces. The reactions at A and B have nothing to do with these forces that are applied. We are just trying to find the resultant of these forces, and then once we have that resultant and we know where it's located on this beam, then sure, then you can go a step further and figure out what the reactions at A and B are and make sure, everything is in static equilibrium. But for this particular problem, we are just finding the resultants of F1 all the way up to Fn, where n is just any number of forces. Okay, so if you don't remember what a force couple system is, let me give a very, very brief, quick sort of explanation. So say you have this beam right here, and on this beam, you have some force that's acting at some point downward. Now, the idea behind a force couple system is that you want to reduce this force or system of forces to a force and couple somewhere along the beam other than where this force is. So let's say I wanted to figure out the effective moment here at point or at the start of the beam. What I can do here is I can say, well, if I move that force here, but then I also applied an equal and opposite force, so all 3 of these forces that are shown, this one, and this one, they have the same value. And what's interesting about these two forces right here is that they are zero, right? If you add a force downward and then you add that same force upward at that same exact point, then these are going to cancel out. However, you could also use this force and say, well, if this force is going down, then it cancels out with this force. And that is perfectly valid. However, when you do that, when you cancel this force and this force, you need to replace that with an equivalent moment at this point right here due to this force to still make sure that the math and everything still works out. So what I'm saying is that we can cancel out this force and then replace this force with a moment over here. And this moment right here, which I will do in green, that moment is going to be equal to this force right here, times this distance. And so what we've effectively done is, because this and this canceled out, we've effectively moved this force all the way over here. And because we moved it some distance, I'll just say x, we need to replace that effect that this force had about this point with a moment right here. And this force couple right here, this force going downward and the moment, is essentially a tactic or a strategy that we can use to solve different problems in statics. So in this case, in our problem for this series or this problem, we're going to use this equivalent moment to figure out what the resultant is and how far that resultant is acting for all of these forces that are acting on this beam right here. So what I'm saying is that these forces right here, they are all going to create some type of a moment about A. And what we're going to do is we're going to figure out what the resultant is. So we're going to add all these forces together. And that force, that resultant force, might be acting at some distance x away from A. And we're going to move this resultant force from its location over to A. But because we've moved it, we need to replace it with an equivalent moment. Now, we're going to use that moment, so this moment right here, to figure out the location of that original resultant force. Okay, so that's sort of the basis of force couple systems. Let's get into the problem, and it should start making a lot more sense as we work through it. So, step 1, understand the prerequisites. Remember, we are only studying the system of forces that are shown above. So we're not actually trying to figure out the static equilibrium of this problem. We're just trying to figure out what equivalent force R can we replace all of these forces with that will have essentially the same effect as these forces if they were just grouped into one single force. Now, we just did a force couple system example down below. And again, we're solving for the resultant of the given forces. So these reactions at A and B don't really matter because they are not a part of this system of forces. We're not doing static equilibrium here. We are doing the resultant of a bunch of forces. Okay, so how do we do that? Well, step 1 is to figure out what the resultant of those forces are. So if we have all of these forces and these forces are going to be given, then we can add all of those together and we can get the value for R. Now, just because we have the value for R doesn't mean we actually know where on that beam that force acts. We know that it's going to act downward and it's going to have some value R, but we need to use the force couple system to figure out what this value, this X value is. Okay, so how do we do that? Well, we replace, just like we did in the example, we replace that equivalent or that R force that's acting downward with a force couple system at A. So how do we do that? Well, that resultant force is going to act down. And if I do R is going down here and then I replace it with an equivalent force here, then you can see this and this cancel out. So what you're left with is R over here, but because R moved over, we need to also replace it with an equivalent moment here. And this right here is our force couple system. So how do we figure out what this moment is? Well, that is this right here. So the moment at A for that resultant force R is just equal to all of the moments that are happening at point A. Why point A? Because that's where we moved R. So how do we do that? Well, it's the summation of R cross each one of these forces. So we're going to take F1 times its distance plus F2 times its distance plus, all the way to Fn times its distance. And we sum all those moments, and that's the moment that we're going to get at point A. And then once we have this system right here, we can use this equation right here and say that, well, if we had that resultant force here, we don't know what the value of x is, but because we know the effective moment that this r causes about point A, we can figure out this value x. So force times distance equals moment. So we have MAR. It's going to be this force right here. We know that r has some value, which we calculated up here. All we need to do is plug in those two values, divide by r, and we get x, which is the distance from point A to that resultant force. And that's effectively all the statics and math that we need to know for this problem. So in the next video, we'll start looking at the algorithm and start talking some code in Python. And I will see you then.